So, in today's class we will start on game trees, and we will see how we can model different game playing situations in terms of game trees, and we will study some very classical algorithms for searching in game trees and finding out when we are in a better position and when we are in a worse position. So, in this on searching game trees, what essentially game trees are, they are OR trees. Namely, we have already studied what AND OR graphs are and AND OR trees are. So, game trees are a special type of OR tree, but there are two types of OR nodes. By OR tree we mean that at a time we will be selecting only one of the successors of the OR node, but which one will be selected will depend on whether it is a min node or a max node. I will shortly explain why we need this kind of a representation. And briefly, we in min nodes we will select the minimum cost successor, and in max nodes we will select the maximum cost successor. Terminal nodes can be winning or losing states, but it is often infeasible to search up to the terminal nodes. So, we will use heuristic cost to compare non-terminal nodes. So, let me start by showing a simple formulation of a game tree search problem. So, let us say we take the example of tic-tac-toe. So, in tic-tac-toe what we have is something like this, right, and the players alternate in putting either a circle or a cross in any of these positions. So, let us say that we start with a configuration where we put x here, right. Then from here, so this is where the one of this is the starting configuration, let us say. Now, it is the move of player B. So, when it is the move of player B, then there are various different moves that player B can take, say out of which this is one, or this is one, and so on. Then for each of these cases player A has a move. So, here let us say player B has a move from this point. In each of these states player A has a move. So, suppose player A makes a move here, then player A can again take one of many different moves. So, suppose if this is the state, then player B can give something like this, or player B can give something like this, and so on, right. Then you know that suppose this is the move that player B has given, then again player A will have turns, but if you look further below this, then you will see that there is a way of playing by which this fellow always wins, because if now the only possible option of this player is to put a dot here, and if that happens, then the other player can put a cross here, and then there is no way of saving the game, right. So, if you look below this subtree, then you will see that for every move that this player makes, the other player has a winning strategy, right. So, now this is the structure of the game tree. The game tree is a tree where every node of the tree represents a state of the game, and nodes can be either a max node or a min node. I have not yet defined what I mean by a max node or a min node, but let us say that one of these types of nodes is for player A and the other is for player B. So, depending on who has the move, we will distinguish between two types of nodes, right. So, we will go right down up to the winning or we can go right down up to the winning or losing combination and then decide what path to take. For example, that if we start from one player, so we will indicate player A by square nodes and player B by round nodes. So, initially player A has a move and that can possibly lead to say 3 moves of 3 different states are possible, let us say. So, this is move 1, move 2, move 3. Now, player B has a move and let us say player B has 2 moves here, maybe player B has just one option here and has say 3 options here, right. Then maybe from here player A can have one option, 2 options, etc. This could be a winning option for player A, right. This may be a winning option for player B, and then again suppose this is the scenario. Now, let us see, we have win here for player B, for player A, we have win here for player A, right, we have win here for player A, we have win here for player A. Now, our objective is to determine that at this point what move we should take, right. So, we will see from here that if this is a win node for player A and since the opponent does not have any alternative choice here. So, this is a win node for player A as well, right. Then here because player A has a choice between these two, so this is also a win node for player A, because if we arrive at this state then player A will take this move and be able to win eventually, right. Then this is a losing, this is a loss for player A, this is also a loss for player A. Now, here because it is the choice of the opponent, so therefore, at this point it is loss for player A, because if we arrive at this state then the opponent is going to push us in this direction, right. Out here it is win for player A, so out here also it is win for player A, right. Now, let us look at this, this is loss for player A, this is also loss for player A, this is loss for player A, right. This is also loss for player A, so this is also loss for player A, right. Now, in this node because it is the opponent's move, so opponent will always push us in this direction. So, this is also loss for player A. So, that means, but here the option is with player A. So, player A can always choose here. So, it is win for player A. So, that means overall in this situation player A has a winning strategy, and what is that winning strategy? It is to take this move, right. If it takes any of the other moves then player B will have a winning strategy. If it takes this one then player B will push us in this direction and it will be win for player B. If it takes this move then again player B will have a winning strategy by pushing us in this direction, right. Is it clear? So, what we have done is we have seen that we can bottom up propagate this winning or losing right up to the top and then decide that which is the move that is to be taken at this point of time, right. The current state is the root of the tree and all other states are look aheads. If I give this move, if he gives that move, like this. Okay. Now, in typically it is very difficult to do this when the game's state space size is very large, like you cannot do this kind of thing when you are dealing with something like chess. For tic-tac-toe, yes, because tic-tac-toe state space is not going to grow too big. So, if you write a program just like this to go right down up to the winning or losing configurations, you can find out at each point of time what is the best move that you have to give, and whether you have a winning strategy or a losing strategy, right. But when you go for games like chess, then you cannot do this because the state space is just too big. So, what we will do is we will expand these moves up to a certain depth, and we will have some heuristic functions to evaluate the position of the game after that many look aheads. So, it means that in chess, let us say I decide to do a 6 move look ahead. So, I look ahead up to 6 moves, and at that level I analyze all the board positions depending on what kind of positional and tactical advantage I have. So, that is where a lot of knowledge will come in about chess, and then I will evaluate those board positions and associate a heuristic cost function with them, which will indicate the probability of my winning from that position, right, probability or the amount of cost that I have to incur. And then we will apply what is called a min max search to determine what is the best move, right. So, for example, let us look at this game tree. In this game tree, we have looked at up to this many number of moves, and then we have found out some cost criterion here, right. Now, what does this cost criterion means? These values tell me what is the cost that I have to incur if I have to win. So, in other words, the lesser the cost, the more are my chances of winning. The more the cost, the lesser is my chance of winning, right. So, we compute the heuristic function in that way. So, we associate a cost which tells me the badness of the state in which I end up. So, for example, if I am here, then the badness is 9, right, badness or goodness depending on how I model it, right. So, we will have two types of node here. One are the square nodes, which we will call max nodes. At these nodes we will try to maximize the cost, and the square nodes are min nodes. In these nodes we will try to minimize the cost. Now, let us understand why do I want to maximize or minimize. So, the kind of games that we are considering here are called zero sum games. Now, zero sum games means that both players are playing for a share of some amount of cost. So, let us say that W is the amount of cost for which they are playing, right. So, this cost is going to get distributed between player A and player B. So, it means that if player A gets more, then player B gets less, and vice versa, right. So, if W, if the zero sum games idea came from the notion that W is 0. So, if somebody gets a positive cost, the other fellow will get a negative cost. So, if somebody has a profit, the other person has a loss, right. And to indicate this scenario, that the advantage of one is the disadvantage of the other, is what we want to represent by zero sum games. Now, this is not always true in practice. It is not always true in practice, because there are cases where the two competitors are adversaries of each other, but the profit of one does not necessarily mean the loss of the other, right. But at the same time there is a large class of game playing situations where actually you are competing for the same resource. So, the win of one is the loss of the other, right. So, for those kinds of scenarios we will have two types of nodes, max nodes and min nodes, right. So, because the loss of one is the gain of the other, it means that if I am trying to maximize my cost, my opponent is trying to minimize my cost. If I am trying to maximize my profit, then the opponent's strategy is to minimize my profit, and this will happen in zero sum games, understood, because my objective and that person's objectives are exactly opposite of each other, right. So, in that case if I have my heuristic function to compute my goodness, so if I evaluate the board position and find that this has goodness of 100 for me, right, then if the total W is 100, then it is goodness of 0 for the other. So, if it is goodness of 50 for me, then it is goodness of 50 for the other, right. So, as I am trying to maximize my profit, my opponent will try to minimize that. So, if you look at this game playing situation here, these represent my profit. So, I am the player A, I am the player A who has to make a move here. So, this game tree has been formulated based on the fact that I now have the move. So, I am player A, I have the move, right. So, when I have the move, I will expand the game tree up to these states, and I will evaluate each of these states depending on how much profit I get. So, these represent the amount of profit that I am getting, right. Okay. Now, let us see what happens. Here my opponent has a move. So, square nodes means my move, round nodes means my opponent's move. So, here the opponent has a move, right. So, what is the opponent going to do here? Will minimize. So, he will pick up 10 here. So, it means that if I reach this state of the game, then I cannot expect more than 10, because the opponent will push me in this direction, right. Likewise, here also this is a min node. So, I will get 9, right. This is also a min node. So, I will have 14. This is a min node. So, I will have 13. Here I will have 2, here I will have 1, here 3 and 20, right. Now, if you look at this layer, this is again a max node, which means that here I have my move. In that case, if I were in this situation, I would know that going this way will give me 10, going this way will give me 9. So, I will always select this direction, right. So, I will go for 10. Now, see, we are also maintaining a mark here, we are maintaining a mark just like we were doing in AO star. Again, out of these two, because this is a max node, this is my move. So, I will select this one, right, and get 14. Here I will be selecting this one and get 2. Here I will be selecting this move and I will get 20. Again, in the min level, if the opponent is in this state, opponent will know that this way I will get 14, this way I will get 10, and remember that the opponent's objective is exactly the opposite of mine, because it is a zero sum game. So, therefore, the opponent will choose this and give me 10. Here also the opponent will choose this and give me 2, right, and here this is a max node. So, it is my choice. So, I will select this one and I will get 10. So, that means that from this configuration, based on the heuristics that I have computed at this level, this is the best move that I have. So, it is, if I take this move, the opponent is going to give me this, then I will take this, then the opponent will give me this. So, that is what I will get, assuming that the opponent does not make a mistake. If the opponent makes a mistake, then actually I gain more, then I will have more profit, because just see, if the opponent instead of going towards this direction, if he had pushed me towards this direction, then I have a strategy of getting 14, right, because I will push it in this direction and then the opponent will have to give me either this or this. So, I will have at least 14, right. So, at any point of time, what I am trying to find out is I am trying to maximize my gains, assuming that the opponent is an adversary who will never make mistakes, and if the opponent makes mistakes, I will get more. If he does not make a mistake, then at least this much I am guaranteed, right, and this is a fair assumption, because we are talking about zero sum games, where my gain is the opponent's loss. Now, there are some optimizations that we can do. We need not actually develop the tree right up to this point, we can actually do some kinds of pruning by going depth first in the tree, and this brings us to some pruning criteria. This pruning criteria and the algorithm called alpha beta pruning was proposed by Donald Knuth many years back. We will study that algorithm and see how we can avoid visiting the entire state space of the game tree. So, again here we will assume that the square nodes are max nodes here, and the round nodes are min nodes. So, let us look at this scenario. Here we are going depth first. So, we find 10 here, right, then we backtrack up to A, then we are visiting B, and let us say that somewhere in this tree we get 14. So, if we get 14 backed up from here, then the claim is that I need not traverse down to C, and the reason is that, see, out here the min node already has a 10. So, if you get anything more than 10 on this arc, then the min node is always going to go that way, because the min node will always minimize. So, if ever the cost of B exceeds 14, if the cost of B exceeds 14 exceeds 10 rather, if the cost of B exceeds 10, then A will always select the arc towards this 10, right. Now, let us see what has happened here. In B, this is a max node, we already have 14, and the cost of the max node can only grow further, because it is max of all its successors. So, if you already have 14, and then there is no point visiting C, because whatever you get from there, B will be at least 14, and A is never going to give this move towards B, it is going to select the move in the other direction, right. So, we can prune off the subtree rooted at C and not search that part of the subtree at all, right. Is this clear? So, this is a case of shallow pruning, where the pruning happens with respect to some parent which is close by, but we can also have deep pruning like we have here. Here my claim is that the subtree rooted at E can be pruned. Now, let us understand why. Here at this max node we already have 10, right, we have 10. Now, out here in this min node we have already got 5, right. Now, by that can we say, okay, out here we have already got 5, right. Now, if you go here further down here, then what are you going to get? You will get something, and this cost is going to be less or equal to 5, right. But if this is less or equal to 5, then it is of no interest for f, because unless f is able to produce a cost larger than 10, the root is always going to divert it to that side. Suppose f is able to manage a cost which is less than 10, right, then when we are in this min node will have a cost less than 10, because if f is not able to get you more than 10, then the min node will always minimize, and so it will always give you less than or equal to 10, right. If f is less than 10, then this is also less than 10, right, but if f is not able to muster more than 10, then there is no point, because the root is going to select this way. Now please try to understand this, that the root is always going to select this arc unless it finds a more attractive option this way, and it can only find a more attractive option this way provided that the successors of this min node are all able to give you more than 10. But if now f is unable to give you more than 10, then there is no point in pursuing f any further. And now what we have found here is that d already has 5 and it will only go further down, right. So therefore there is no point in checking this, because this branch at least is not going to give f more than 10. If f takes this branch, it is not going to take more than 10, right. So we can prune it off at E. Is this clear? What is the difference between? Okay. When we are talking about deep cutoff, we will now introduce a couple of bounds. We have to formalize this, right. We will have to formalize that when do we do this cutoff. So deep cutoff actually gives us an idea. See here, this 10 is just not the immediate parent of D, it is the parent's parent's parent, and this can happen even if you drag D right down up to several more levels of min and max. So let us formalize that, then you will understand why this deep cutoff is useful. So we will consider two bounds on the states of the game. One is the alpha bound. The alpha bound of J is the maximum current value of all max ancestors of J, and we will stop the exploration of a min node when its value falls equals or falls below alpha. So let us look at a scenario here. I have this. So there are other states. So I am just looking at one path. Okay. These are the other paths which I have already visited, and these are the paths which I have not yet visited, right. So this is just one path of the game tree, right. So in this way so let us say that this is the min node J, right. Now the alpha bound of J, or let us say alpha of J, is defined as the current maximum value of all max ancestors of J. So it is the values that are backed up here. So suppose this has backed up something like 20, and this has backed up something like 5, let us say this has backed up 10, right, and so on. So it is the current maximum among all these. Now, whenever the value of this j, the current value of j falls below this alpha, we will not explore the remaining successors of j anymore. Now, let us understand why. Now, consider that max ancestor which has this value alpha j, right. So, in this case let us say this is the one. Now, the moment this fellow's value falls below that value, we know that there is no point exploring this any further, because this the game is never going to come to this state, because the max node here has a strategy of taking you to a node which has at least 20. What do I mean by having a value 20 here? It means that from this node I have already found out some strategy of reaching cost of at least 20. If the opponent makes a mistake, probably more. If the opponent does not make a mistake, then at least 20. So, I have a strategy of going to a node which gives me at least 20. Now, here I am finding that when I am visiting j, the cost has already dipped below 20, and if I explore further, it may dip further or be at most 20. It is not going to exceed 20, because this is a min node. So, the node here is never going to try the strategy of coming to this node. So, the strategies for visiting this node are of no interest from this layer, because there are better strategies already. So, this move itself will not be selected if it is the case that we have to end up here. If it is the case that we have to end up here, then out here it will not select this move, right. Okay. So, we do not explore this any further, but does it mean that we have already chosen this one? No, because along the other paths from these max ancestors, we might still get some cost which is larger than 20, right. So, we are just pruning off this min node, we are just pruning off the min node here, we are not doing anything with respect to the other max ancestors of this node. Is it clear, right? So, in the min nodes, what we are checking is whether its current value has fallen below the value backed up in the max ancestors of the node. If it has, then we do not further explore that min node, we just backtrack to its previous max parent. And in a min node we will update beta, because beta, the beta bound of j is the minimum current value of all min ancestors of j, and in a similar, by a similar argument we can say that exploration of a max node j is stopped when its value equals or exceeds beta, and in a max node we update alpha, because if you see that the value of beta is the minimum current value of all min ancestors of j. So, we will continuously keep on updating beta when we are in the min nodes, and we will keep on updating alpha as we are exploring a max node. Is this all right? Now, before we go into the algorithm, okay, right. Now, when do we return, when do we backtrack? So, in both min and max nodes we will return when alpha is greater than or equal to beta. Now, see, this criterion is actually encompassing these criteria, that exploration of a min node is stopped when its value equals or falls below alpha, and exploration of a max is stopped when its value equals or exceeds beta. Because you see the beta value that we are maintaining here is the minimum of the min node that we are currently exploring and all its mean ancestors. Now, the very fact that we are still working with this node means that the previous beta value is not greater than or equal to alpha. The previous beta value is still less than or equal to alpha. That is why we are still visiting this, right. And when this value, the value of this mean node falls below alpha, that is where the beta value is also fall below alpha. So, that is where we will stop exploration. So, in this, so this is the criterion which covers both of these conditions, that in min or max nodes we return when alpha is greater than or equal to beta, right. Yes. No. See, we have gone a long way from that. We were talking about terminal nodes when we were talking about small games, right. That is where we can go right down up to the this thing. Now, we are talking about heuristic functions in the level where we are cutting off. Are you talking about them as terminal nodes? Are you referring to the ground level nodes as terminal nodes, right? Yes. So, when you are in the terminal nodes, that is where we will, that is where the induction basis will come. So, in the, as you go down recursively, that is where you will reach the basis of the induction. So, you will start assigning your initial values at that point. We will come to the algorithm, then I will explain. So, let us do one thing. Let us work out the alpha beta pruning on one of the on an example. So, let us say that this is the initially we do not have this graph, initially we do not have this tree. So, we are just developing it as we are going depth first. So, in alpha beta pruning we are going depth first and we will do the pruning as and when we require. So, we will start from here, okay. Then we will take, we are going depth first. So, we will go this way, generate this state, then this way, in this way, this way. So, let us say that we are working with a depth look ahead of so many moves, right. So, when we have made so many moves, at this point we will evaluate the board position. So, at this position let us say we find that the board position is 10, right. So, then we will backtrack. Now, this answers your question, that when we have reached the level of look aheads, we will backtrack. We will backtrack with the value of 10, right. So, now the beta value of this node is 10, right. The beta value here is 10. Then I look at this state and let us say I evaluate this and find 11. Then what am I going to back up? I am going, because this is a min node, it is going to back up 10, right. So, now the alpha value here, so here the beta was 10, now the alpha here becomes 10, right, because alpha is the values at the max ancestors that we are maintaining. Then we will go this way, right, again depth first, then we go this way depth first, and let us say at this point we find 9. Now, note that here the beta value is now 9 and the beta value has fallen below the alpha value. So, we will prune here, we will not visit this side anymore. And why? Let us see why we will not visit here. This max node has already got 10 and in this min node you have 9 and it may only dip further, right. So, we will not, there is no point exploring this anymore, because the max node is always going to go this way, because this is going to give you 9 or less, and this is already 10. So, we will always take this link, clear. So, therefore, this is pruned. Then let us continue. We go back here, what is this going to back up? It is going to back up 10, right. So, now our alpha is 10, beta is 10, right. Then we go this way, again we will go depth first. So, this way, this way, this way, and we find 14 here, right. So, now the beta value here is 14, alpha is 10. So, we are still in business, right, we are still in business, because if we can, the moment we will when will we be out of business? If we find that this fellow's cost also exceeds 10, because then this node here is never going to push us in this direction. It knows if it pushes us in this direction, it will be in trouble, right. So, let us see. So, we will still traverse. So, we will take this one. Here we find 15. Now, the moment we find 15 here, what do we have? We will have 14 here, and that means that out here the alpha value is 14, right. Alpha is 14, beta is 10. So, we have again reached the pruning criterion, and therefore, there is no point in checking this. And why so? Because if you see that this max node has already got 14 and this can only grow, right. And so, in this min node we will never take this way, because if we go this way it is going to be at least 14, but if it goes this way then we know that it is at most 10. So, this fellow is trying to minimize. So, he will always, it will always push us in this direction, right. So, therefore, what do we back up here? 10, right. Again we have alpha equal to 10, beta equal to 10, right. Then we go in this direction, again depth first, depth first, depth first, depth first, right. Here we find 5, right. Now, the beta value here is going to be 5. Now, again alpha is 10, beta is 5. So, we have a pruning criterion, right. What is our pruning criterion? Whenever we find alpha is greater than or equal to beta, this is the pruning criterion. So, that has happened again, alpha is 10, beta is 5. So, we prune this. And what is the reason of that? Because we know that if you come in this direction, it is not going to be for this node, because if you come here you are going to get 5 or less, and this fellow already has a strategy of getting 10. So, even if it chooses this link, it is not going to be because of this node. So, therefore, there is no point visiting this node further, right. Whether this is 5 or 3 or 1 does not matter, all of them are equally bad, because we already have 10. Okay. So, then what is this backing up from here? 5, right. Okay. So, alpha here is still 10, because the max ancestor here has 10. So, alpha is still 10, and again we have, what do we have as the beta out here? 5, right. So, no, we do not have 5 here, 5 was here, but we have already backtracked from there. So, it is only on the mean ancestors, right. Okay. So, we will go in this direction and we will come here. See, there is still a possibility that you get something more than 10 from this side. If you get something more than 10, then this still remains an attractive option. So, if you can get more than 10 here, more than 10 here, then this link will become better. So, we come here and we get 4, right. So, again we have beta equal to 4, alpha is 10, pruning criterion applies, we prune here, clear, and then we go back. So, this is going to back up 5, right. If this backs up 5, then here in we will have beta equal to 5, again alpha is 10, beta is 5. So, we can prune off this whole part, because this gives us that if you take this root, you cannot get more than 5, and if that happens, then this in this max node we will never consider this move, because if we consider this move, the opponent has a strategy of giving us 5 or less, but we already have a strategy of getting 10. So, we will never choose this move. So, no point visiting this part at all. So, this whole subtree gets pruned, and we finally come here with alpha equal to 10, and we will choose this one. So, the best move at this point is this, which is what we also found out by doing that whole bottom up stuff, but this alpha beta pruning helps us in getting rid of significant portions of the game tree, right. Any questions? Okay. So, now let us have a look at the algorithm. So, in this algorithm, if j is a terminal, then we return Vj equal to Hj. So, if we are at the leaf level, after the number of look aheads that we have done, we return Vj is equal to Hj. Vj is the cost that we will eventually return at the root. So, at a state j, Vj is the best cost that we can get from the point of view of player A. So, all costs are with respect to player A. If j is a max node, then for each successor jk of j in succession, we set alpha as the maximum of the existing alpha which it has inherited from its parent. See, this is a recursive procedure. So, the alpha that you are getting is coming from your parent, right, and what is the definition of the alpha value? It is the maximum value that is among all the max nodes, including this current max node and its max ancestors, right. So, it is the maximum of the existing alpha and the value that I obtain by recursively calling Vjk with alpha and beta bounds, right. So, this alpha and beta bounds, because they are coming from the ancestors, so we can recursively call these procedures with the alpha and beta bounds being passed down, right. We are passing the alpha and beta bounds down into the recursion, and then we apply the pruning criterion, that if alpha is greater than or equal to beta, then we return beta, otherwise we continue. And then if we have finished with all the successors, then we have not yet pruned anything. So, we have visited all the successors, then the best cost that I have in the max node is the alpha cost. So, we return alpha, right, and we do a exactly complementary stuff for the min node. So, for each successor jk of j in succession, set beta equal to minimum of beta and Vjk alpha beta. In the min nodes, we are maintaining the value of beta, and again we check if alpha is greater than or equal to beta, then return alpha, otherwise continue in this loop, and if you have finished this loop with all successors, then return beta, right. So, what I would ask you to do is, you can either write a small piece of code to check this out on some game like tic-tac-toe or any other game that you can think of, and also to handwork this algorithm on one game tree, right, so that you have confidence in what is meant by this alpha beta pruning procedure. Okay. Now, So, with that we come to the end of the lecture on game trees. Do you have any questions on?
So is it that if when we are pruning, sir, is it that when the opponent makes a mistake, is it that we'll still never go to those parts which are pruned?
If the opponent makes a mistake, you may go to those parts which are pruned, but in those cases you will definitely get a profit more than what you would normally get.
So, but if we have pruned that part, we don't know the path ahead of it.
No, so you will again see that is the next move. See, what are we doing this analysis for? To determine what move we will make now.
So, we won't use the paths we have decided?
No. We will not use those paths because we will assume that the opponent is intelligent. The opponent will not make mistakes, right. So, we are taking into consideration the worst case scenario with respect to the opponent, right. So, we will choose our move based on that, right. Now, if the opponent makes a wrong move or the move which I had not expected, then what we can do is we will again be in a max node after 2 levels of moves. So, from there we will again expand out the game tree and do the analysis again, right, and then determine which would be our best move there. But what we are assured is that the best move that we get from there is going to be at least as good as what I originally had planned for. That is because the opponent has made a mistake. So, my min max value can only be more than what I had obtained here, is not it?
So, was it the same case in the previous one where when we are not pruning? At every step where we do evaluate, because that is not necessary, because once we have decided on the paths, we need not evaluate after every step, we know where to go exactly.
No, in the previous case means
when we were not pruning.
when we were not pruning, yes. So, in that case what we were doing is we were looking ahead right up to the leaf level, which is the number of lookouts that we are doing.
And here we know all the paths. Once
Yes.
we know what opponent B is choosing, we know where to go after that.
No. I think I must clarify that. This is the current decision that I am taking. If the opponent puts me here, I will again do that many move look aheads, right. See, why am I restricting the number of look aheads? Because of the computational complexity involved, because the state space grows very fast, particularly in games like chess, the branching is very large. So, the state space will really blow up if you look 15-16 moves. I mean, beyond that it's even 15-16 moves is phenomenal, right. So, you cannot really afford to go much further below. That is why we are looking ahead that many number of moves. But when I have already played a couple of moves, I have taken my move, the opponent has taken the move, I will again do an analysis of that. Now, if you look at the expert level at which you are playing with the chess playing program, that actually determines the number of move look aheads that it is trying. So, if you look at a greater expert level, then it is using more knowledge and it is using more look aheads, right. So, it will take more time also.
In the problems like tic-tac-toe or chess, they are not able to visualize how exactly we will be putting a value to a particular situation.
So, in tic-tac-toe we do not normally do that because it is a small game. So, you can actually expand it right up to the winning or losing configurations, right. But in chess, that is a $1 million question, that is the determining the heuristic function is the key factor there. So, they do a lot of things, they keep history of different games and find out that from this position what is how many winning scenarios were there, and they try to follow also some of those existing patterns, or they can actually evaluate then, say a simple thing could be the number of pieces that you have, right. The number of pieces that you have in your board is one of the issues, right. Actually what happens is there this is not a single objective scenario. In a chess playing scenario, there can be multiple criterion which determine the tactical and positional advantage that you have, right. So, there is some work on that, actually some of my own work is on that, on how to extend multi-criteria searching algorithms to game playing situations. So, I can give you the citation if you want to take a look later on. Right. So, we will now move into a completely new topic. I think we have done a lot of search. Now, we will move into a chapter on knowledge based systems, logic and deduction. So, this is a new thing which we will start working at from this thing, and we will see that it is a combination of search and deduction which will make up for almost the majority of the different kinds of activities or computational requirements that we have in AI. So, in this we are going to study a bunch of different techniques for representing problems in logic and also techniques for deducing new facts and new rules from the existing ones. So, the important things are representation of real world scenarios and reasoning with logic. We will study firstly, to start with, a logic called propositional logic. Then we will see add further things into the propositional logic, namely quantifiers, to get into first order logic. Then we will study inference mechanisms in propositional logic as well as in first order logic, and we will see that depending on the expressibility of your logic, the cost that we have to pay is in terms of the computational complexity of reasoning in those logics. So, for example, while finding out the satisfiability of a propositional logic formula will be shown to be NP complete, the question of the satisfiability in first order logic or the validity of a formula in first order logic will be semi decidable. So, there will be cases where the problem will be unsolvable, like you have studied the halting problem of Turing machine. That was one of the problems that you came across which is unsolvable, right. So, we will see that inference in first order logic is also semi decidable, in the sense that in one direction we can say yes, but the other direction, the no answer, can be undecidable, right. So, we will look into those things. We will study some classical techniques called generalized modus ponens for reasoning in first order logic. We will study some kind of forward and backward chaining mechanisms for inferencing. These are popularly used in all the deduction systems, and we will also study a technique called resolution and give you an overview of logical reasoning systems.